Hi everyone, this is going to be our last video for the semester going over chi-squared and ANOVA. Sorry, this should say squared with a D. There we go. So these are two more kinds of hypothesis testing. So we saw the t-test that was used to compare one group to a mean or two groups to each other. We have chi-square. This is the Greek letter chi. We have this chi-squared test of independence. And what this checks to see is if two factors are independent of each other or not based on a distribution. And then we have ANOVA, which stands for analysis of variance. And what ANOVA is used for is to compare means of multiple groups. We'll say more than two. You can do it for two groups, but more than two is where this is really intended for. These are the two that we're going to look at. And a lot of the calculations and formulas for these are very long to do by hand. So we're going to use software to do these. We're going to do all of these examples in R. So we'll walk through the examples and talk about how you set these problems up and how you interpret the p-values and all that. So for chi-squared, we have our null and alternative hypothesis. Your null hypothesis is always there is no relationship between the two groups. And your alternative hypothesis is the opposite of that, that there is a relationship. So null hypothesis, this is the alternative hypothesis. There is a relationship between the two groups. And then we move forward with the test, we get a p-value and all that. So let's go through an example. A survey asked a random sample of, this should be young adults. Where do you live now? Where do you stay most often? Below you'll find a table for all the people in the sample, both men and women, classified by their age and where they live. So when you're doing problems out of the homework, you'll be given a table and then you can translate it into R. So here your null hypothesis is there's no relationship between, there's no relationship between the two groups. So in context, there's no relationship between age and where young adults live. The alternative hypothesis is there is a relationship. So it's the same thing, it's just you replace the word no with the word a. And that's an easy way to switch between. So we're going to go ahead and make the data in R. Now, if you're looking at this from a textbook working on a problem, then you'll see the table and it'll show you how to make all these values, but we have it all in here ourselves. So we have people living with parents, people living with another person, people have their own place, people that live with a group, or people with other living arrangements. And I'm going to combine these all with the command rbind. This combines them all as rows, so they'll be stacked on top of each other. So parents will be one row, this will be a row, this will be a row, this will be a row, and so on. And you'll see what this looks like all complete, and the different age categories I'm going to name the columns of this matrix. So when all is said and done, this is what it looks like. We have these as the rows. That's what our bind did, that combined all these as rows into a nice table like this. And then this assigning column names, I named all of these columns. So ideally, so what'll really happen is when you're working on the exercises, you'll see a table and it'll already look like this in the book, and you will translate it into R. And this is what our table looks like. So to do a chi-square test, this saves us a lot of work to do by hand. We use the command chi-square, C-H-I-S-Q .test. You know, before we had like t.test for t-test, now it's chi-square .test. The data set and $p-value to get your p-value. And a significance level was not stated here, so we're going to assume a significance level of 0.05. And we got a p-value of 6.98 times 10 to the minus 35, right? So that's really 0.0000, you know, 34 zeros and then 698. Notice it gave us this warning here that the approximation may be incorrect, and that's because with any type of statistical hypothesis test, there are some underlying assumptions. One assumption for this is we need to have a significant or a large enough count in each of these groups. So age 19 and parents, age 20 and another, all these we need to have a good sample size for. But you see things like this, 2 and 3. That's a very, very small sample. That's not a lot of data to make assumptions or come to conclusions based off of. And that's why it's saying this may be incorrect, because an assumption is potentially violated here with not having a large enough sample in all of the groups. So we calculated the p-value. Since the p-value is less than 0.05, we reject the null hypothesis. Evidence suggests there is a relationship between living arrangements in young adults. So we rejected the null. The null was that there was no relationship in favor of the alternative. And you can look up the formulas for this if you'd like. It would take a very long time to do this by hand, especially with bigger tables. Let's do another one. Popularity of computer, video, online, and virtual reality games has raised concerns about the ability to negatively impact youth, although the existing literature has been inconsistent. The data in this exercise are based on a recent survey of 14 to 18-year-olds in Connecticut high school. We wish to see if there's a relationship between playing video games and grades. All right, so the null hypothesis is going to be there is no relationship. Right? Null hypothesis is always no relationship, because you don't want to assume there is a relationship, right? If you assume there is one, then there's no reason to do this test. There is no relationship between grades and whether or not one plays video games. And then the alternative hypothesis is that there is a relationship. So let's piece this data together. People that played games and never played video games, combine them, give column names for their grades. One group of A's and B's, a group for C's, and a group for D's and F's here. And we end up with this table. So we want to see, is there a relationship between whether or not they ever played video games in high school and what kind of grades they got. We do the same procedure. chi-square.test your data and $p-value to get the p-value. And for this, again, our alpha we're going to assume is 0.05 because we're not told, and our p-value is 0.034. So the p-value is less than 0.05, so we reject the null hypothesis. Evidence suggests there is a relationship between grades and whether or not one plays video games. So what this doesn't say that if you play more video games then your grades are better or worse. It doesn't answer that question. It just says, does there seem to be a relationship between the values in this table? Okay. So that's the gist of it for chi-square. Just different sized tables and such, but that is the main idea. Again, we could get into all the technical details of what's going on behind the scenes, but those examples are very cumbersome to work out by hand, especially if your tables are quite large. So next we're going to move over to ANOVA, analysis of variance. And like I mentioned before, ANOVA is used to compare multiple groups. So just like in a two-sample t-test, where your null hypothesis is that there's no difference between the two groups, your null hypothesis for ANOVA is that there's no difference on average between the groups, whatever those groups may be. You'll have the context. And then we can do the same trick for alternative hypothesis that we just did, where we can copy paste this and then just change the word no to the word A. There is a difference between the groups. So looking at this example, this comes from one of the CSV files uploaded called insulation. We're looking at kilowatt hours used in a given month by a heating system of a sample of houses as a function of 5 different insulation thicknesses. We wish to see if there is a difference in the amount of energy used with different amounts of ceiling insulation. So the idea being, okay, does it matter how much ceiling insulation we have to determine how much energy we use? Because if the answer is no, then you would just use the cheapest insulation. If the answer is yes, it becomes a question of, okay, do I want to invest in better insulation to save on energy? So our null hypothesis is there's no difference in the amount of energy used with different amounts of ceiling insulation, and the alternative hypothesis being there is a difference. So the only difference between these two statements is we've changed the word no to the word A. That's the only difference here. So we're going to read in this data set. I have it opened in another window on my screen. You can see the insulation thickness data set. So when we look at this data, I'll type it out, MD. We see all these different ceiling insulation thicknesses, 4, 6, 8, 10, 12. But the thing is, these are numbers, but we want to treat them as groups. These are different groups that we're looking at. We want to consider these as groups, not numbers in a specific order. So we're going to end up specifying it to make R not register these as numbers. And then we have here how much energy is used in kilowatt hours. One way to see if there may be a relationship is to make a plot. So let's plot type, which is the thickness, against energy usage and see what that looks like. It gave me an error because it didn't fit in these margins. Let me open that up a little bit more. Okay, here we go. So generally it looks like as insulation increases, it looks like kilowatt usage goes down. Generally that's what it looks like. So from the plot we think there may be a relationship between these, between insulation and kilowatt usage. So the ANOVA will tell us if this is true. Is there a difference statistically in the means somewhere among these groups? And one thing I noted earlier is that to do an ANOVA test, we like to think of this variable as a group and not a number. So to do that, we specify it as a factor. Okay. By default, it's going to assume it's a number because it's entered as a number. But if we want to treat it as a category instead of a number, we're going to type factor. And when you run the plot with that, it looks a little bit different. It ends up giving you distributions in all of the groups. The 5-number summary with the box plots is another way you can look at it. And when we are doing the ANOVA tests, it's not as nice of a command and then the p-value like we've been doing before. Here we use the command AOV for analysis of variance, and then you do your dependent variable tilde your independent variable. Okay, so similar to linear regression. So my dependent variable being energy usage, and then my independent variable being my type, and my type I specify as a factor here. So I'm saving that as something called MA for my ANOVA, just to be easy. And then we can look at the summary of the test. We can look at the summary. And this gives you a lot of information, but all we care about is the p-value, which is this value here. So PR for probability. Remember, p-value is a probability. So our alpha level was not specified, so we assume 0.05. And our p-value is 2.1 times 10 to the minus 8, which is 0.1234567. So the p-value is less than 0.05, so we reject the null hypothesis. Evidence suggests there is a difference on average in the amount of energy used with different amounts of ceiling insulation thicknesses. So statistically there's a difference. So then it's up to you to make the decision, okay, do you want to spend more money to get better insulation in your home to save energy? So there's a follow-up question there. So this only says that there is a difference somewhere among these groups. It doesn't say exactly where the difference is. To do that, you would follow it up with another test that's called a Tukey test. And that is beyond the scope of this course. But there's a follow-up test called a Tukey test that'll help identify which groups are different than other groups. Let's clear this. And then a note here, the analysis confirmed the suspicion from the graph. In the graph, it looked like there was a relationship, and now we confirm that statistically the means of the groups, there's at least one that's different. Here we're studying whether or not appraisers for the same company are appraising similar properties at similar prices. So say you're buying a house and you have someone come, an appraiser whose job is to determine the value of the house based on several factors. If two appraisers are appraising similar properties very, very different, that has implications, right? If they overvalue it, then the buyers may, or the sellers may ask for more money, but the buyers may not be able to be approved by the bank for a higher amount. On the reverse side, if they appraise it too low, then that hurts the sellers, because then the buyers are not going to want to pay what the sellers are asking. So you want to make sure that your appraisers are doing their job consistently among each other. Our null hypothesis is that there is no difference in who the appraiser is with the value of similar properties. And the alternative is there is a difference on average in who the appraiser is with similar properties, with the value similar properties are appraised at. So our independent variable here are the different appraisers. I'm going to read in this data set, the appraisals data set. Let me find it on my computer. All right, I found it. All right. So what this data set looks like, we have appraiser 1, 2, and 3, 3 appraisers, and the prices they're evaluating houses at. And these are in thousands of dollars, so $183,000, for instance. We can go ahead and look at a plot to see if we think there's a difference. plot appraisers on the x-axis as a factor, and then price on the y-axis. And we have this here. It's not as clear of a picture as the one before where we saw a clear trend. So the question is, are any of these different? It looks like this is generally higher than either of these. This, you may say, it looks kind of lower, but are they different enough from each other to say that they're statistically different, right? They're never going to be perfectly the same between each one. So the answer is, the question is, are they statistically different? And that's what the ANOVA is going to answer. So we have a guess. Maybe 2 is high. Maybe there is a difference somewhere, but we will see. So I'm going to do the same thing, AOV, for analysis of variance, your dependent variable, and then tilde, your independent variable as a factor, and I'm saving that as MA my ANOVA, and then I'm going to do summary of my ANOVA, and I'm going to look at the p-value. My p-value here is 0.137. Again, an alpha level was not specified. And 0.137 is greater than 0.05. So we fail to reject the null hypothesis. We fail to reject the null hypothesis. We do not have sufficient evidence to suggest there's a difference on average with how different appraisers are valuing similar properties. Which, if you're the owner of this appraisal company, that's good. That's what you want. You want to make sure your employees are performing appropriately. So if the p-value was small, then that would say the appraisers are not appraising properties more consistently, and you'd have to implement employee training or something like that. Okay. Last example here. We're studying the effect of having a product placed in one location versus 2 locations at a store. For example, do sales increase on gum or chapstick if they're placed at checkout lane in addition to their usual aisle? So all the grocery stores here have an aisle where they have gum and chapstick and such like that, but they also have gum and chapstick at all of the registers at checkout. So the question is, does that actually increase the sales if we put them in 2 locations? Right? Surely we know in advance the answer must be yes, or else stores wouldn't be doing this, right? They wouldn't pay people to stock items, the same item in more than one place. That's more work. They wouldn't do that if it wasn't profitable. So we have a guess in advance that the answer should be yes. So we're going to run a test to confirm. We're going to read in the data. We're going to read in the sales file, which I have on my computer. Okay. So if we look at what this data looks like, we have whether an item was placed in 1 or 2 locations and how many units of it sold. We can look at a plot, and we can see it looks like items placed in 2 locations instead of 1 have higher sale volume, right? They're selling more. Overall, it looks higher, right? The minimum is higher, the first quartile is higher, the median's higher, third quartile is higher, the max is higher. So on all metrics, group 2 is higher, which we assumed already, which we kind of guessed. We used our common sense to determine that. So to do the formal ANOVA test, we can put sales on the x-axis, or not on the x-axis. Sales is our dependent variable, so we put it first. Tilde your locations as a factor, and we can look at a summary. And we get a p-value here of 0.0051. So our alpha level was not specified, and our p-value is 0.00521. So since the p-value is less than 0.05, we reject the null hypothesis. Evidence suggests that there is a difference on average between the number of locations an item is placed with the amount of units sold, which means it is in a grocery store's best interest to do this with certain items, right? It's a open question whether it makes sense to do 3 locations instead of 2. Does that increase sales more or not? Who knows? But these are kind of different kinds of analyses and studies that stores can do. We looked at things restaurants can do before in this class to see if they can boost sales in any way. So this will be your last homework. Homework 8 will cover chi-square and ANOVA, and that will be due by the end of this week. And keep in mind, we do have the final exam at the end of this week also, so please do send me the time you would like to take that. Take care, everyone.